Hi everyone! Today, in this video and the next, we're going to see two things having to do with pseudorandomness, extractors and expanders. Pseudorandomness is the study of generating something that looks random while using little or no actual randomness. This is a huge field and we could spend a whole quarter on it. We only have one class, so we're going to stay pretty high level. The point of this video and the next one is just sort of to give you a taste of what's going on in this area. Our first pseudorandom object is a randomness extractor. One motivation behind extractors is that we've been spending all quarter analyzing randomized algorithms assuming that we have access to uniformly random bits. But where do those uniformly random bits come from? Unless we have access to something weird in quantum, it's unlikely that our quote-unquote random bits are going to be truly random. So with that motivation, here's an informal definition of an extractor. An extractor is something that takes a weak random source, so something with a little bit of randomness in it, but that's not perfectly random, and is going to extract an output that is close to uniform. To help it out, it's going to be allowed to have a short d-bit seed of true uniform randomness. In order to define an extractor formally, we need to say what we mean by weak and what we mean by close. So let's do that next. First, what do we mean by weak? Intuitively, we want it to mean that we can have some weak source of randomness, something that's kind of random, but not perfectly random. So here's the way that we're going to quantify it. We're going to use something called min-entropy. So given a random variable x with support d, the min-entropy of x is defined to be h sub infinity of x, that's how we'll denote it, and it's equal to the minimum over all x in the domain d, of 1 divided by the log base 2 of the probability that the random variable x is equal to little x. In pictures, that looks like this. So suppose that this is the probability mass function for some random variable x. What this definition is saying is that we should look at the sort of the L infinity norm of this probability mass function. And this point here is going to be 1 divided by 2 to the min-entropy of x. Thus, the larger the min-entropy of the random variable, the smaller this limit is, and the more and more flat the distribution is going to become. So more min-entropy, closer to uniform, intuitively. We say that a random variable x is a k source if the min-entropy of x is at least k. In other words, for a k source, this level here is at most 1 over 2 to the k. So notice that if x is a random variable defined on 0, 1 to the n, so it's n bits long, just like our putative source up here, then if k equals n, and x happens to be a k source, aka an n source, then x is uniform. Thus, if we have an n source here, we have a perfect source of randomness, and if we have a k source for some k less than n, we have some weak source of randomness. So that's going to be how we're going to quantify weak randomness for our purposes. Next, recall that we wanted the output of this extractor to be quote-unquote close to uniform. How do we quantify close? We're going to use the total variation distance that we've seen before. So just as a reminder, the total variation distance between x and y, if both x and y are random variables with support d, is defined as this. So it's 1/2 the L1 distance between the probability mass functions. That is 1/2 times the sum over all x in the domain of the absolute value of the difference between the probability that capital X is equal to little x minus the probability that capital Y is equal to little x. In pictures, it looks like this. So suppose that this is the probability mass function for x, and here's the probability mass function for y. Then the total variation distance between x and y is given by this volume here, or actually half of this volume. That is, we have total variation distance between x and y is equal to 1/2 times the yellow stuff. Now that we have those definitions, we can give a formal definition of a randomness extractor. We say that a function ext that maps 0, 1 to the n cross 0, 1 to the d to 0, 1 to the m is a k, epsilon extractor if for all k sources x on 0, 1 to the n, the total variation distance between the output of the extractor when given the source x and a uniformly random seed, and just the uniformly random distribution on m bits, should be at most epsilon. So here, this notation u sub d, this is the uniform distribution on d bits. Mapping this definition to the picture we had before, here is our k source x. This is our seed, which we're assuming is uniform. And this output is equal to ext of x, ud. And our goal is that this output here should be epsilon close to uniform in total variation distance. That's what this says. So what should our goals be in terms of parameters for this extractor? Well, first, we would like d to be as small as possible. That's because for our seed d, we need actual uniform randomness. And of course, the whole point of this motivation was that we don't actually have access to that. We'll come back to that a little bit more on the next slide. The other thing we want is that m, the length of the output, should be close to k plus d. That's because intuitively we have like k bits of randomness coming in here, d bits of randomness coming in here, and ideally we'd be able to squeeze all of that randomness out here. So we'd like to be able to get close to k plus d bits of randomness, or at least close to randomness, out of the other end of the extractor. Okay, so you might be wondering, why do we need a seed? Isn't that cheating? If the whole point is that we don't have access to uniform random bits, why are we allowed to use them for a seed? Actually, it turns out that without a seed, this task, as defined on the previous slide, is impossible. So to see this, suppose that we did have an extractor that did this. So say that we had an extractor that took in a k source on 0, 1 to the n, no seed, and just outputted an output. So the picture looks like this. Here's 0, 1 to the n. Here's the output 0, 1 to the m. And the extractor maps between them. Now let's consider breaking up this set here into two chunks. So I'm going to break it up into the half where the first bit is 0, and the half where the first bit is 1. That is, these are bit strings of length m, and these are all the ones that start with 0, and these are all the ones that start with 1. So let's color the ones that start with 0 yellow, and the ones that start with 1 blue. Now if I go back and look at the preimage, because ext is a function, I can similarly divide up the preimage in some way. It might not be half and half, but there's some division. Let's say it looks like that. And let's say, without loss of generality, that the preimage of the yellow set is larger than the preimage of the blue set. That is, if I let S be the preimage of the yellow set, so this is all the points x that map to some bit string whose first bit is 0, that let's just assume, without loss of generality, that the size of S is greater than or equal to 2 to the n all divided by 2, also known as 2 to the n minus 1. And now let's consider the random variable x, which is uniform on the set S. Since x is uniform on a set of size at least 2 to the n minus 1, that implies that the min-entropy of x is at least n minus 1. In particular, this is a nearly uniform source. In other words, it's a k source for all k less than or equal to n minus 1. On the other hand, I claim that the output of this extractor is nowhere near close to uniform. To see this, let's draw a picture of the output distribution. So here's my domain, and let's break it up into the yellow set and the blue set. That is, over here are all of the bit strings in 0, 1 to the m, where the first bit is 0, and over here are all of the bit strings in 0, 1 to the m, where the first bit is 1. And if we look at the probability mass function of the extractor on the source x, it's going to look something like this. That is, the support is entirely contained on the blue set, and it's 0 on the yellow set. But now let's consider the distribution that we want to compare it to, the uniform distribution. That looks something like this. So it's just flat. And the total variation distance between these two distributions is given by this volume here. In particular, this volume here contains all of this volume, which is just a half, because it's half of the mass under the uniform distribution. So this implies that the total variation distance between the output of the extractor and the uniform distribution is large, greater than or equal to 1/2. In particular, if we wanted an epsilon k extractor for any k less than or equal to n minus 1, and any epsilon strictly less than 1/2, no dice, we're out of luck. We really need a seed if we want to do that. Okay, so given that we need a seed, we can at least hope for a small one. We'll see in a minute that actually if the seed is small enough, then we won't actually need any uniform random bits. Basically, we'll just be able to exhaust over all possible choices of them. Fortunately, such good extractors do exist. So here's a theorem. For all positive integers n, and all k between 0 and n, and for all epsilon greater than 0, there is a k epsilon extractor ext, which takes in an n-bit k source and a d-bit seed, and outputs m bits that are epsilon close to uniform, with the following parameters. M, the number of output bits, is equal to k plus d minus 2 log 1 over epsilon plus some constant. And d, the length of the seed, is equal to log of n minus k plus 2 log 1 over epsilon plus some constant. In particular, this basically gets exactly what we wanted. Let's suppose for a moment that epsilon is some constant, like 1/10 or something like that. Then all this stuff is a constant, and what we're left with is this. And this is basically what we wanted. The number of output bits is k plus d, which makes sense because the number of input bits of randomness was about k plus d. And the length of the seed is small, logarithmic in n. We'll see in a moment why logarithmic in n is a good answer. So that's great. We're not going to prove this theorem in class, but actually you have the tools to prove it yourself if you feel like it. The proof follows from the probabilistic method. That is, take a completely random function x from this domain to this range, and that'll do the job with high probability. Of course, that might be kind of unsatisfying. If the whole point is to use an extractor to avoid using randomness, then using randomness to create the extractor might seem a little bit circular. But fortunately, there are also good deterministic explicit constructions of extractors. In particular, if you want an explicit construction, so here explicit means that it's a deterministic construction that I can sort of efficiently manipulate, then I can't get quite these parameters, but I can get close. In particular, at least for constant epsilon, I can get m equal to 0.99 times k, where 0.99 can be replaced with any constant you want that's less than 1. And the seed length can be big O of log n. This is assuming that epsilon is constant. Let's say 0.01 or something like that. So this is still pretty good. I'm certainly not going to talk about the proof of this theorem, the explicit construction, in this class. It's much more tricky, but see the lecture notes if you want some pointers to it. Okay, so extractors exist with seeds that have log n bits in them. As I mentioned before, this is actually pretty good. The reason is that if there's only big O of log n bits per seed, that means that there are only polynomial in n number of seeds. So even if we can't draw such a seed uniformly at random because we don't have any random bits to work with, we can just try them all. To be a little more precise, suppose that we want to use some randomized algorithm A, which takes some input that I've just called input here, and also takes a random string R. So when I use this notation, what I mean is that I'm thinking of A here actually as a deterministic algorithm, whose randomness comes all through this input string R, where I think of R as being uniformly random bits. Now suppose that this randomized algorithm, which I'm writing as a deterministic algorithm that takes a random input string R, suppose that it's correct with probability at least 3/4 over the choice of R. And I would like to use this randomized algorithm, but unfortunately I don't have uniformly random bits to plug into R. All I have is some k-source X. What am I going to do? Well, I can use an extractor, like we saw before, even though I don't have a seed. How do I do it? Well, basically I'm just going to exhaust over all possible seeds. So that is, consider this algorithm. For every seed S in 0, 1 to the d, now if d equals log n, or big O of log n, there are polynomially many such seeds, so this is computationally feasible. So for each possible seed, I'm going to run my randomized algorithm on the input that I care about, as well as on the output of the extractor, on my k-source, and on that seed S. At the end of the day, I'm going to have run a bunch of times on a bunch of different random strings, or pseudorandom strings, and I'll just take the majority vote over all of the seeds. Now, why does this work? Well, since at least 3/4 of the seeds S here are good, majority vote is going to be correct. There is a slight issue here that this thing here isn't exactly uniform, it's epsilon close to uniform, but it turns out that this will work out fine as long as epsilon is small enough. So that's why it's okay that we were allowing for this cheating seed thing, because as long as the seed length is small enough, we can just exhaust over all possible seeds and get rid of the need for it. Okay, so that's it for this video. As a quick recap, extractors take a weak random source, a source with low min-entropy, and turn it into close to uniform random bits, perhaps with the help of a uniformly random seed. Moreover, good extractors exist. The fact that they exist you can probably prove on your own, fun exercise. The fact that there exist explicit ones, quite a bit trickier. Alright, thanks for watching.